So what can we learn from our image compression examples? Well, here's a first lesson. If we think about how our factorization of our large matrix representing the Swedish flag looked like, it looked something like this. We took our matrix A, and then we expressed it as a linear combination of column vectors multiplied by row vectors. Notationally with math, the way we would write this is we take a scalar called sigma 1, and then we multiply by a column vector called u1, multiplied by a row vector, which is represented by a column vector v1 conjugate transpose. Then we have a next term, sigma 2, which is multiplied by column vector times row vector. And we keep going until we get to a last term, which is sigma r, multiplied by column multiplied by row. So the idea is that a decomposition that takes this form would allow us to losslessly compress the data inside of our original matrix A. And then a second lesson tells us that we could drop terms from this sum. So maybe if we went all the way out to R, we get an equality. But if I start dropping terms from this sum, I get not an equality anymore, but an approximation. So dropping terms from the decomposition further compresses the data, but this could come at the expense of quality. So all of this motivation is designed to introduce us to the concept of singular value decomposition. So what is singular value decomposition? Singular value decomposition is a matrix factorization. It's a matrix factorization of the form A equals U sigma V conjugate transpose, where A is any m by n matrix, and here the rank is going to be called little r. So we can take any m by n matrix, and then we can look at the rank, which is called r here, and find what's called a singular value decomposition. And this is U times sigma times V conjugate transpose, where U is an m by r matrix. So the number of rows of U is the same as the number of rows of A, and the number of columns of U is the same as the rank of A. And this U is special because it satisfies the desirable equation U star times U, or Gramian of U, is the R by R identity matrix. What this is saying is that the columns of U are orthonormal. Then we're multiplying by a matrix sigma. This is a diagonal matrix whose entries are positive scalars, which are listed on the diagonal in decreasing order. So this is the diagonal matrix where the first diagonal entry is the positive number, which we will call sigma sub 1. The next number is a number that does not exceed sigma 1, but could be equal to it, called sigma 2. And then we keep going until we get to the last diagonal entry, which is sigma sub r. So sigma is a diagonal R by R matrix where the entries on the diagonal are positive numbers listed in decreasing order. Finally, V, which is the last ingredient in a singular value decomposition, is an N by R matrix. So the number of rows of V is the same as the number of columns of A, and the number of columns of V is the same as the rank of A. And here, V is a matrix satisfying V star V is the R by R identity matrix. In other words, the Gramian of V is the identity matrix. Again, what this means is that the columns of V are also orthonormal. So a singular value decomposition is a factorization of any m by n matrix with rank R as U times sigma times V conjugate transpose, where U and V are matrices satisfying the equation Gramian equals the identity, and sigma is a diagonal matrix whose diagonal consists of positive numbers listed in decreasing order. So when we have a singular value decomposition, the scalars on the diagonal of capital sigma are called the singular values of the matrix, and the sum of the form A approximately equals first singular value multiplied by first column of U multiplied by first column of V conjugate transpose plus sigma 2 multiplied by second column of U multiplied by the second row of V conjugate transpose, all the way down to sigma sub k multiplied by the first column of U multiplied by the kth column of U multiplied by the kth row of V conjugate transpose, is what's called the rank K approximation of A. So let's look at this with an example. So the definition of singular value decomposition involves some technical details. Let's see this in practice. So here what we have is the data of a singular value decomposition of a 2 by 3 matrix A. So we've taken this 2 by 3 matrix A, which evidently has rank 2, and we can see this by noting that the two rows are not multiples of each other. And we've expressed A as the product U times sigma times V conjugate transpose, where U is a 2 by 2 matrix with orthonormal columns. Sigma is a 2 by 2 diagonal matrix with diagonal consisting of positive numbers listed in decreasing order. And then V is a 3 by 2 matrix whose columns are orthonormal. And note that in the factorization, we're taking U times sigma times V conjugate transpose. So the matrix we're looking at here is the conjugate transpose of V, not V itself. So in this context, what are the singular values of A? Well, the singular values of A are exactly the diagonal entries of sigma. So in this case, the singular values are 5 and 3. The compressed sum that comes out of singular value decomposition here is an expression of the original matrix A written as a linear combination of column times row vectors. So the first term here will be the first singular value, which is 5, multiplied by the first column of U, which is 1 over root 2, 1 over root 2, multiplied by the first row of V conjugate transpose, which is 1 over root 2, 1 over root 2, 0. Since this is a rank 2 matrix, to get the fully compressed sum without losing inequality, we need a second term, which is the second singular value, 3, multiplied by the first column of U, which is 1 over root 2, negative 1 over root 2. And then we multiply by the second row of V conjugate transpose, which is 1 over root 18, negative 1 over root 18, 4 over root 18. So this is the compressed sum that we get when we factor A according to a singular value decomposition. We're taking A and we're expressing it as a linear combination of two expressions where we take a column times a row. We could look at the rank 1 approximation of A, and the rank 1 approximation of A is not an equality, but it's an approximation. Here what we're doing is we're ignoring the second term of our compressed sum, and we're only including the first term. So here we're looking at 5, which is the first singular value, multiplied by the first column of U, 1 over root 2, 1 over root 2, and then we multiply by the first row of V conjugate transpose, 1 over root 2, 1 over root 2, 0. When we multiply these quantities together, we get a new 2 by 3 matrix, which is not the same as the original matrix, but it does have the same size. And the idea is that this is a rank 1 matrix that approximates this rank 2 matrix. So even though these two matrices are not the same, we say that they are approximately equal to one another.